Okay, a formal good morning to everyone. And that was Rod Stewart and Maggie May. And we've already selected the song to end, so that's good. Yesterday, Sarah was sharing with me some of the things she was doing in a class in which they were talking about the national debt. So I thought that was an interesting way to start this section because what's shown on the website is, and I Googled this in the source of all wisdom, Googling, and so we're going to cut to the document cam, Jennifer, if you would, and this was as of March. So this date on this is March 3rd, 2009, if you look at the monitor. 10.9 trillion. Okay, so that's where it was in March. So I have, again, if you'll give me that just for a bit more, 10.9 trillion. So it's time to do one of the mini reviews. What's a trillion? How do we decide on a trillion? Give me the shortcut. This goes all the way back to large numbers and scientific notation, right? How many bars are involved with trillion? The tri meaning 3 bars, okay? 3 bars on top of a what? M. So we have an M, bar, bar, bar. And what does the M stand for? Ah. Good. Both answers good. One's not technically correct, but incurrent. No. In the Roman system, M is for 1,000. And in modern newspaper print, million. You got to be careful. So the M is 1,000, and then the bar reflects what? Additional thousand, thousands, thousands. So I'm going to put in the extra zeros. So now I have my trillion, correct? So as we name it, thousands, millions, billions, trillions, and the tri referring to the 3 bars with the M. So how would I write this number in scientific notation? 10.9 trillion. Okay, good. 1.09 has to be there, but now that is in essence times 10 to get to the 10.9, correct? And then the trillion is times 10 to the what? 12th power? 1, 2, 3, 4. Times 3 is the 12th. This is the 1 that we don't often write. So what's your answer? 10 or 1.09 times 10 to the, add the exponents. 10 to the first times 10 to the 12th, add the exponents, so 10 to the 13th. Agreed? When you multiply the bases, you add the exponents. That is our national debt as of March. Well, let's see how much it's gone up. Oh, you wish it was going down. The hope is that it's going to go down, right? Well, now, Barack has promised that I think at the end of 10, or is it 8? I think he was saying if I'm in here for 8 years, he's going to try to get it down to zip.
Well, I think he set up a 10-year plan.
Oh, a 10-year plan. Okay, well, I'll go with that. I'm going to go ahead now, and I'm going to go what's called the national debt clock. Oh, yes, such a beautiful representation. No less in red. Let's cut. Isn't that impressive? Red for in debt. It's gone from what? 10.9 to now 11 T per trillion. So that means our current, I need that up a little bit longer, Jennifer. I can't remember it that well. It's a bad number. 039. And this is going to hold just for a short period of time. It'll change. 956, 978, 596. That seems rather insignificant, that last 31 cents, right?
Yeah, I know.
Okay, but how would you say it in a verbal form? 11 trillion, 39 billion, 956 million, 978,196 and 31 cents. Depressing. Okay? Just a thought. There's the big thing about AIG, right? And they've spent a few million in bonuses, right? About how many million in bonuses? About 100 million? The question is, do I think they'll give it back? I will take the fifth. I have no idea. But what is 100 million as a percent of that? Ah, but you do. Let's say that AIG, I think they've given $1 million to 100 employees, roughly. So that's 100,000 millions, and I'm just using this as a vehicle to review large numbers, because that's part of this lesson that we are doing today in 6.3. Scientific notation, large numbers with decimals, and that's precisely what we're doing. So what is this as a power of 10? 10 to the 8th? Do we agree? You have 8 zeros, so 10 to the 8th power. Fair enough? Now, I want to divide that by, and I'm going to round this off, if you don't mind, to the nearest trillion. And it's 11 trillion. Agreed? Okay, so a trillion was what? 10 to the 12th. So I have 11 times 10 to the 12th, correct? Okay so far? Now I want to get this as a percent. So let's see what we can do here. If you cancel the 10 to the 8th with the 10 to the 12th, we'll get what? 10 to the 4th, agreed? So this is a 10 to the 4th here. So far, okay. And to the nearest 10, 11's like 10. True? The nearest 10. So this is like 1 over 10 to the 5th. But that's really like 1 over 10 to the 3rd times 100. Will you agree with that? This is your percent. And 1 over 10 to the 3rd is 0.001. So, in terms of the national debt, this is just 0.001 of a full percent of the national debt. Now, what was the bailout that the government provided to AIG, roughly speaking? About, say, 250 to 300 billion, and growing, I think. Agreed? So, now the question. We know what this is the national debt. Very small part of it. So we didn't really, the bonus in terms of the national debt, 0.001 of a percent, not much. But let's say that AIG was given $250 billion. So that's thousands, millions, billions. And, Jennifer, if you can, there we go, thank you. And they paid out 100 million in bonuses. What percent of the bailout went for these bonuses that everybody's upset about? How about $1 million? Thank you, James. $1 million would make more sense. Okay, more dollars. Now, in terms of this, what do we have in the numerator? Power of 10. 10 to the 8th still. Down here, what do we have? Let's do this in scientific notation. 2.50 times 10 to the what? Okay, 3, 6, 9, 10, 11. Okay, so that gives you 1 over 2.5 times 10 to the 3rd. Do we agree? Okay, we're getting closer. I would like 100 here, correct? To get a percent. So I'm going to take a 10 from here and get 1 over this, and I'm done with what I needed, and we're going to get a number that we've seen before. Okay, so that's 1 over 25 times 1 over 100, so that's 1/25 of a percent. Now, part of the problem is, of course, we're using money that was from the taxpayer. But my point is, this is 1/25 of 1% of the total bailout went for those bonuses. Interesting in terms of arithmetic. Okay? So that's my start for lesson 6.3. Well, it's $1 million is a lot of money to be giving away. I mean, that's the whole, when Sarah and I talked about this over dinner, her comment was, yeah, but they screwed up the company and they're getting $1 million. That's not fair. And I tried to point out it was only 1/25 of 1%, and that didn't make it. So, coming back center, Jennifer. The reason I bring this up has to do with some information in 6.3, and so that's what I'm going to come back to. And this is at an old area of familiarity. We've been there before, so let's take a look at what we're doing to the document cap. And it's multiplying decimal numbers, exponents, with decimal bases, and scientific notation is understood but not said. So the first thing that I would like to just reference, because we've just talked about it here, comes all the way over to applications on page 435. And some of the work that's being talked about here involves the language of taxes and of so on. If you look down at property taxes on example 10, and I'm not going to do much with these as far as our homework, because I'd like to focus on just the skills and the drill for the moment in this particular section. But country property tax. And so this is related to what we are talking about, where you are getting taxed on something. And we talk about that bailout, and coming off there for a moment just to tie together with this unit again. The solution, by the way, to this problem with AIG is the government's thinking of taxing that at 90%. So if you got a bonus of $1 million, the government's talking about maybe taxing it at 90% if they won't give it back. So 90% means 10% left. So your bonus would be at what? If you had $1 million, okay, take 10% of that and you have 100,000. If that maybe is more realistic, and then somebody said, maybe we should just tax it at 100%. We're going to get it back one way or the other. And of course, the idea here is you without calculators, are going to be doing things that involve decimals. So now, what I want to do is tie together with this where we've been before. I've tried to do that in the board with scientific notation. So now, let's look at page 432. This is one of the objectives. Okay, standard form numbers in scientific notation. And what have we called that instead of standard form? Positional notation. So this is a particular problem, a little bit smaller number than the one I just put in the board. What would you read this as? 62 million? 910,000. Three of you did very well. I hope the rest of you know that number. Now, if you wanted to do this in scientific notation, what was our rule before, so we can pull some things together relative to what is done in this book for what we did? Okay, you put the decimal after the first, what do we call that? First digit, but more important than that, the first non-zero digit. Because what I'm going to do, as I go over to the sideboard on this now, Jennifer, okay, we are going to have, in contrast, I'll write the number we have there, 629100000. But I'm going to contrast this to this number. If I had something like this, where do I want my decimal in this case? Okay, between the 5 and the 6. Okay, you couldn't say after the what? The first digit. That's where we make the statement after the first non-zero digit. And then, I've got the decimal in both of these, so I'm going to have a 6.291 times 10. This is going to be a 5.63 times 10. How did I decide the exponent? Michael?
Negative exponent for a decimal and positive exponent for a whole number.
Okay. Positive exponent over here for a whole number. And Michael said a negative exponent for a decimal, but I'm going to be cautious here because technically there's a decimal in this number at the end. So you have to be a little bit cautious there. Well, if the number is less than 1. Okay, I'm going to, I think, translate Jessica's statement, which is as follows. Here's where I'm locating it in scientific notation. Now, I want to go back to where it was. It was at the end, and that's why it's technically a decimal. And how far did I have to go to get it back? A total of 7 places, hence 7th power. Here, to get it back, I had to go to the left, hence negative exponent, and I had to go 1, 2, 3, 4, hence negative 4. Okay? That's how we did it before. And now I'm going to leave this, and we're going to go back to the document cam. And in terms of what's done in the statement in the text, I think you're going to find it very comfortable. As we go down to the bottom of that page for your reference, it says, move the decimal point so that the number's absolute value is greater than or equal to 1. Now, this is in dealing with negative numbers also, so I want to look at that for a moment. And then it says, write the decimal number multiplied by 10 to the nth. Well, as you read that in the bottom of 432 and go through the process, the only difference is I could allow a negative value. So if we think of this again, the statement here, to write a standard form number whose absolute value is greater than 1 in scientific notation. We talk about a large number, the whole argument. And so, Jennifer, I'm going to create problems for you because we got camera 2 over there. Yeah, I know. So, would you thank you. Bring camera 2 back up here to our national debt. So if we go to the national debt, what I want to bring to your mind here, and this is where we have a philosophical question. Is there an agreement that either this number or, as Jennifer moves over, this number, that those are big numbers? We agree that that national debt is big. Everybody sort of goes with that. But if I talk about 532, is that a big number? No, relatively speaking. So when do we use scientific notation, generally speaking? With large numbers. Now, what's being stated here, as long as the number in absolute value is more than 1, we can go to scientific notation. So if I think in terms of a large number, what about these? Well, if this was in red, right? So if you're a bookkeeping major, an accounting major, what would you put with this number? A negative sign. Because that's debt, right? So on the ledger, that's negative. So if I'm going to play that game, then I would want to rewrite that in scientific notation. And what would often be done, now remember this was 11 trillion. Okay, so I would be inclined to say minus 11 trillion, and that's the way we would write it. And I suspect, going back to James's observation, that if you see an M in a newspaper, you mean million. If you see a B, you mean billion. If you see a T, you're supposed to understand it's trillion. Do you realize 5 years ago, if you'd said trillion, most people would have no idea of what you were talking about, and now they feel comfortable with it? That's scary. Okay, that you feel comfortable with hearing $1 trillion and you don't run screaming. Can I write this in scientific notation now? The trillion was what now? 10 to the 12th. So this is minus 11 times 10 to the 12th. Is that in scientific notation? No, because I don't have the decimal here. So this is negative 1.1 times 10 to the 1st times 10 to the 12th. That's getting back to the fact that this will be 10 to the 13th. This was in scientific notation with a negative number. So the statement the author's making, first think of it in absolute value. That gets rid of the sign. Is the number more than 1? Oh, yeah. 11 trillion is more than 1. Then, locate your decimal point after the first digit, because if it's a large number, you don't have a 0 in front of it. This is assuming for what? Very large numbers. But in our world, we have very small numbers. So the other number I wrote on the sideboard is the kind of thing we see in computers. That might be the time it takes for a single calculation. It might be the width of a space on a computer chip that is done with microscopes at this point to create them. So as we come back to the document cam, Jennifer, and I'll bring that down a little bit tighter. So this is to write a standard form number, translate positional notation, and of course the idea is that the decimal point so that the first digit is between what? 1 and 10. Well, we had an 11, so we had to write it so it was a 1.1. Then we put the decimal point there. And then we multiply by what? A power of 10 so that, and I'm going to have to come off there just for a moment, Jennifer, as I pull this down. Okay, multiply by a power of 10, where n is the number of places to get back to what? The original decimal position. I use the phrase in Math 10, getting back home. So, Jennifer, camera 2 again, please, to the sideboard. Jennifer is going to get a workout. It'll help her deal with the dexterity she needs. Back to the document cam, if you could, there for a moment. And as we go to this number, again the argument. We went from here back to here. And if you go to the left, it's negative. And if you go to the right, it's positive. Now, the statement made by the document cam, as we come back there just for a moment, to the original position, n is the number of places, what I wish the author would have said there. If you go to the right, it's positive. If you go to the left, it's negative. End of story. Nothing particularly new there. So what happens if I take these two and were to multiply them together? How would you do it? If I take these two numbers and said I want to multiply them together. Well, part of the answer is do this. Now, Jennifer, if you could, I need to tweak just a bit to see the 6.29. Now, this is a kind of problem in another lifetime that we had in physics and chemistry classes without calculators. Okay? And we had to get rough answers for the problem. So I have a 6.291 times 10 to the 7th multiplied by a 5.63 times the 10 to the minus 4. And what we would do is we'd round this off roughly to 6.3. So we'd say 6.3 times 10 to the 7th. And I'd round this off to a 5.6 times 10 to the minus 4. Now what can I do? And again, I'm thinking now of associative property. Okay, before we get to there, associative property. As it stands, I have two factors here, and I could rearrange with associativity, commutativity, the properties, and I ultimately could do what is being asked. That is, multiply these two together, and then multiply these two together. And a reminder that when we multiply with the same basis, what do I do to the exponents? I add them. If you wish, think of it as a subtraction. 10 to the third, correct? So this whole process I'm talking about here, and this part, is going to be times 10 to the third. And if you were just to estimate here, you'd say somewhere between 30 and maybe 35. So somewhere in that area. So I would take these two and simply multiply them together. And this was something we could do with a thing called a slide rule without knowing where the decimal would go, because it would not locate a decimal point for you. But we would do a problem in a very similar way, and of course that is the 3, 7, 8. Then we have the 15, the 31, and we have the 8, the 12, the 4, 5, and the 3. And now, this is the next part that's in this review that the author does, in which if you have 2 digits after the decimal here, you should have that same number of digits after the decimal there, and avoids the what? The left-right movement. We'll look at that in a moment. So the answer, and I'd like to clean that up just a little bit because that's looking messy. I'm going to have 35, and I said it was between 30 and 35, and the text will ask you to make estimates. And this, again, is not an exact answer, because what did I do at the beginning? I rounded off. Is it in scientific notation at this point? No, because the decimal's after the second digit. If I wanted it in scientific notation, you would do this. That's where you have the 1 here. 3.528 times 10 to the first is that. Still times 10 to the third. So you have to play with the exponents. And so I have what? 10 to the fourth in scientific notation. If you want it in positional or standard form, the digit's going to go, decimal's going to go over 4 places. And so all this becomes 35280, which was, strictly speaking, an estimate because I did what? I rounded off before I started. So if you wanted to do this without the round off, it's a messier problem longhand, and you wouldn't in your right mind do this without the calculator at this point, where you would actually take, as we slide over, Jennifer, to the 6.291 and actually multiply that by the 5.63, and it's going to affect the answer as we slide back a little bit. So this is an approximation. We got it? Okay, back to the document cam if you would, Jennifer. That's the first part. A lot of review, nothing new. Then, what I just mentioned in terms of multiplying with decimals, and again, remember, the idea was to multiply with decimals. And I'm going to come to a statement. I have to hunt for that for a moment. There we go. This is a statement on page 429, and again, what I've tried to emphasize to you as we've gone through this Math 20 with this particular book, every step of the way, it is exactly what we did in 10. The verbiage, I could not have written a book more in keeping with what I wrote in the Math 10 than what's been done here. And I don't have the energy to do a book like this for Math 20. But if you did, look at the statement on page 429, because it's written exactly as we talk about. Stack the numbers. You understand what we mean by stacking. We just did that. And note, and this is something that I gave you as a disclaimer earlier, you don't have to line up the decimal point. Off there for a moment. When do you line up the decimal point? Add and subtraction. So the addition and subtraction line up the DP. Multiplication probably misleads you if you try lining them up. Then ignore the decimal. Multiply them just like they're whole numbers. Then this is the thing I've tried to do, and it's interesting. Place the decimal point in the product so that it has the same number of decimal places as the total number of decimal places in the original numbers. Otherwise, you go ahead in the factors. That's the phrase. Now, that translates. Let's come back to that for a moment, Jennifer. And then I'm going to go back to the side. Leave that there for a moment. The argument. And this is where I've shared with you the frustration of decades. And I don't have a good answer for you. I've tried so many different things, and there is no magic bullet. Every semester for more years than I'd like to admit to, moving a decimal point around screws up people. They don't do it well. They forget it. And it's the battle I have in the 210 groups right now. We argue that there are 2 digits after the decimal point here, total. So we'd like 2 after the decimal point here. So I locate the decimal so that they're the same number of digits here after the decimal point as there were in the original factors. I did that for a long time, and I'm back to moving the decimal point around, because moving it to the left or the right. And remember our rule of thumb. If you divide by a power of 10, you move the decimal to the left in places. If you multiply by a power of 10, you move the decimal to the right in places. And that seems to be working better than what the author's trying here and what I've tried forever to do, just the number of digits after the decimal point. But it's consistent with where you've been. So this is a case where, as I said yesterday, and this gets back, Kim, to the kind of question, if something's working for you, don't change it. Even if it's not getting quite the way it's asked in the book, if it's working for you at the moment, stay with it so you're confident, you feel good about it, and then, when you see the shortcut, it'll be comfortable. Michael? No. Okay. Any question there before I go back to the document camp? Okay. Back, Jennifer, if you would. So we have that as our statement. Again, nothing new. So as we come back center and we go a little bit further ahead, we've dealt with the idea of multiplying. We've talked about scientific notation. We reviewed that. Okay, and so nothing's particularly new there. There is one problem that I'm concerned about, and it's this one, which is an example on page 431, in which we are taking something to a power with a negative and a decimal point involved. And let's look at our options. And this, Kim, gets back to, I think, your position as to what's going to work. But just long enough, Jennifer, I can get it, please. Negative 0.04. Do I need this first 0? No, it's an optional, correct? Where do we use it, typically? And that looks bad. Looks very badly done. In the medical area, you are correct. Okay, because we want somebody to be aware. Is that the third power originally? Okay. We would like the person who's doing the reading to recognize the decimals coming. And if we had something like a 0.5 and you don't put that 0 in front, they don't see the decimal, they see it as 5, and they give an overdosage. And in pediatrics, that can be lethal. Okay, one very straightforward approach. The 3 says write that factor in a product 3 times. Now this is straightforward, hardly thinking about it, doing that. And it'll work. We have 3 negative factors, so my answer must be negative. No way in the world I want to do that problem that way, even though I could do it. I just cannot discipline myself to do that. So what I'll do is first recognize it's a negative sign. Now, what's that in scientific notation? Come on, scientific notation. You can do that faster. 4 times what? 10 to the? Whew, that took a lot more than I wanted. Isn't that easier? Okay, now I'm going to ask you to remember something from the algebra. If I have a, b to the nth, what is it? Okay, a to the nth, b to the nth. And if I have a to the m to the n, what is it? No, not a-m-n. A to the m-n. No, not amen. A to the mn. Got it? I can use that because this 4 is 4 to the first. Bless you. Are we ready? So that's going to be 4 to the what? Third. Multiply the exponent coming through. This is a to the nth.
Oh, yeah, it is 4 to the 3rd.
Okay, I will slow down. I'll redo this.
And then 10 to the negative 6.
And then 10 to the negative 2 to the third. This is my A. This is my B. So I'm taking A to the third, B to the third. And 4 to the 1 to the third is 4 to the third. 10 to the minus 2 to the third is 10 to the minus 6. What is 4 to the third? Okay, we have disagreement. I'm not going to vote. 4 times 4 is 16. Times 4 is 64. And it's negative because I had, in essence, the negative factor to an odd power, hence negative, times 10 to the minus 6. Okay, give me the answer now. Negative what? Now, where's the decimal understood here? This is not in scientific notation. But, no, because the decimal had to be after the 6 to be in SN, right? Be in scientific notation, the decimal had to be there. I had it after the 4. But this still tells me to do what? 6 places to the left, because, just a reminder, 10 to the minus 6 is the same as what? Try again, Robert. Yes, 1 over 10 to the 6th. So I'm dividing by 10 to the 6th. Decimal has to go to the left. So this is 0.0000064. That's it. Yes, that's easier. You debate that. Okay, I could sit there and say 0.04 times 0.04. And yes, I could say, well, that's 16, but then I have to have this. Agreed? Because I have 4 digits after the decimal point. Then I get to multiply that by 0.04 again, which I know is going to be a 64. And that's going to be what? 1, 2, 3, 4, 5, 6. So I have to have 4 zeros here, and I get the same answer. And you like that? Couldn't sell this, huh? I just don't like all, yes, I don't like all those zeros. Okay. Okay, this was the more popular solution. It is a valid solution. This is leading to better things. This is where you want to be. This is where you can be without pain. Here's where I want you to go, and pain can be good. I'm not selling that. But the idea is try to go to where you're using these exponents. Okay, so I'm going to leave that on the board. There are always going to be very different ways of doing the problem, and you'll be very pleased to note, as you look on page 431, your favorite solution is the one presented. I don't like it. Okay? Because it's not leading to the future. It's a step to the past. Yeah, back to the future. Well stated, Emily. I'd like you to be heading towards algebra, not back to 10. 70's ahead, 10's behind. Oh, wisdom of Isaac. Stay in the present. Well, you could, but you know, there's a fascinating thing about you either go ahead or you go behind. You hardly ever stay where you are. So if I have a choice, I'll go ahead. Okay, well, that was an easy call. Well, let's see if we can then make something out of this a little more interesting. On page 433, here's a nice product of two monomials. Now, there's nothing to be said for this that we haven't done before. I'm going to rewrite that, Jennifer, over on the side. I'm starting to run out of room, but that means we'll be innovative. We may go to paper, go to the other wall, who knows. The problem could have been done this way, and I'm going to ask you, would you have any problem doing? You would not. You haven't even let me finish it. Good grief. Now, if I write that, would you have any problem with it?
Wait, no, you just, no.
I've heard a yep and a nope. What could you do? You could take 2 times 3 and get 6, and y to the 7 plus 8, and my hope is that based on what we've done the last week or two, that wouldn't be a problem. I would like the intermediate step for the moment because it reminds you of what you're doing. Okay? Because with an hour of sleep, James, you might multiply these exponents. Now, in this problem, we made it harder. We did this for the next problem. And that made it harder because it had what in it? Fractions. Fractions make life more difficult. So what's the answer here? There we go. 1/2 times 1/3, folks. Come on now. 1 over 6, right? Y to the 7 plus 8, so we get 1 over 6, y to the 15th. Not when we were just working with fractions. Remember we had 3 different sets of problems we were going to do. One lived with whole numbers. We just finished a set where we lived with fractions, and so we wrote our answer with fractions. 1/6 is a perfectly nice fraction. But you could go to decimals, and that's what we're doing in the new chapter. So that's why as we go back to the document cam, we note that instead of just a 2, we have a what? 2.1 y to the 7th, and I need that up there for a moment longer, Jennifer, so I can write 3.43 y to the 8th, and now I've gone from whole numbers to fractions to decimals. So what are you going to do here? You're going to take 3.43 and multiply by the 2.1 to get that part. Okay? Kim.
Why are you relying on that with multiplication?
Okay. Kim's noticing I had them lined up a little bit, so I won't. No, it doesn't matter, and I was just not paying any attention to whether I did or didn't. They don't have to be. But you could, if you like it. Your choice. And you could get me the answer, correct? What's the answer? Quickly. 1023? Do we agree in that? Multiply it out, please, quickly. Let's see if we agree. 7 sounds better to me because this is about 3.5, and this is about 2. That would be a 7. So I agree with Erica. At least with the 7, and I like the point, but I'll go with a few more digits. You agree with the 7?
Yes.
Okay, I've got 3 of you in agreement. That's not making me real happy. 7.72? 7.2. 203. Are we finally getting there? I like the 3 at the end because 1 times 3 would be 3, so that makes me happy. And then what am I going to do with the y parts? Same as before, and say y to the 15th. Now, that's supposed to make this a problem in this section. Nothing algebraically is any different. All we've done is change the coefficients to decimals. That is debatable, whether it's harder or easier. Now, let's go back to Marisol's comment. 1/6. Why wouldn't you want to do that as a decimal there, Marisol? Tell me about 1/6. It's a decimal fraction. I want it as a decimal fraction. What is a decimal fraction? It repeats itself. What gets repeated? Well, it's 1/2 of a third, right? And a third is your 0.333 forever. So what you're going to do is divide that by 2 and get 1.16666 forever. And that's a really awkward thing to put in front of that y to the 15th. So 1/6 would be typically. And then one more comment. Most of the time you would see this written this way. Y to the 15th over 6. Just so it's a common fraction, not a number multiplied by y to the 15th. Michael.
With those decimals, if they were fractions, would they be mixed numbers?
Oh, nice. You're not supposed to say, oh, no. That was a good question. 2.1 is 2m1/10. Hence, it is a mixed number immediately. And this is 3 43/100ths. So a mixed number. So yes, I could translate that into one of these. And you could, but we won't. It could be done, and it would be painful. Okay, so we'll leave it the way it is. Okay, let's keep coming back. Let's back center for a moment. So you have a number of problems in the set like that. They aren't too bad. But finally, let's look at something where a couple things are put together. These are just sort of at the tail end of this section. I'm on page 434, which I remind you is a palindromic number again.
Yeah.
You remember a palindrome? Yes, Natalie?
Not prime.
What's a palindrome? You don't remember. Okay, read it forwards or backwards, you get the same number. So 434 was palindromic. I got to tell you a cute story from yesterday. One of the students, and I won't say who, she would be embarrassed, got stopped for speeding, trying to get to school in time from my class, which made me feel bad. Lee. It was a 55 zone. She was doing 88. And I suggested to her that she should have gone 1 mile per hour faster. Why? Because she could have made a very strong argument to the CHP that might have given her a humorous result instead of a ticket. What speed should she have gone to make it a more interesting problem? Instead of 88? 89. Why? Oh, you've forgotten. No, well, it is a prime, but that wasn't the answer I wanted. Okay, let me go with this. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89 are Fibonacci numbers. And the ratio of 89 to 55 should be the golden mean at 1.6180339. And she could have told him, I'm trying to achieve the golden mean.
He would have looked at her like she was crazy.
Well, he might have laughed instead of writing the ticket. Of course, at 90, I think it becomes very serious if you're at 90. They take your car away and things like that.
No, they just write the ticket for $5 so you don't.
Okay, let's go back to page 434, a palindromic number, which is not a Fibonacci number. What are you going to do here? Well, it's just that exponent, the intermediate step I like. The 0.2 to the third power, the a to the second to the third. That is very similar to what I was just doing. And just a minute, I need to get something to hold the corner of this book up. And I want to leave that there for a moment, Jennifer, because that is coming back to this general statement right here. Sorry, Jennifer, I didn't telegraph that well. But this is the structure. So what is being done is you have a product, and you write each factor to that power. Look again at the document cam. And that's precisely what's been done. Now, what I don't like is you look at that. This really was something b to something and then to the n. So I would have preferred to have that b to the something to the n. And all that's been done as we go back to the document cam, you've multiplied the 2 times the 3 on the exponent for a. Okay, come back to this for a moment. A few weeks ago on NPR, are you familiar with the math guy on NPR?
No.
You just haven't been listening to enough NPR. It's a really neat thing to listen to. That and reading the newspaper, which may or may not exist in a few more months. National Public Radio, 91.3.
Oh, NPR.
In National Public Radio, 91.3 FM. Okay, we got that straight. 91.3 is not in scientific notation. So 91.3 should be 9.13 times 10 to the first in scientific notation. You'll remember it that way. Keith Devlin, D-E-V-L-I-N, is the math guy out of Stanford University. And he got asked a question because what is the big push in education right now about algebra? Eighth grade. Eighth grade. The idea is that by the time you get out of eighth grade, you've had a full year of algebra. And there's been a lot of flack about this because the argument is there are an awful lot of students who just won't get out because there are people who do algebra and people who don't. Okay? Now, it's been an argument that's been going on for a few centuries. Comment. Keith Devlin was asked, well, what is algebra? And I liked his comment, and it amounted to the following, that arithmetic is about numbers, multiplying them, and algebra is about the structure of numbers, sort of generalizing what you do with numbers. And this is the generalization to what we have in the document cam, where you actually do it with numbers as we go back to the document cam. So one's looking at the structure, and the other's looking at what you do with numbers. So this is sort of a generalization. And this is where people get hung up a lot because the first reaction is, well, what's A and what's B? It represents some number. Okay, so if I tell you I have some product of two numbers and I want to take them to some exponent, this is a nice general way of saying it, writing a mathematical expression. So again, one of the dilemmas you're having as you make this transition from math 10 to 70 in what we do in between at 20 is to go from numbers to general structure. And so we tie together these nice reviews of all these rules we've used all last semester, and we try to push you forward, which is a long-winded defense for what I was doing here. This is the general structure. And at some point you, I hope, get a warm, fuzzy feeling doing that. That you do this and say, yes, that feels good. And celebrate. You aren't there yet, I suspect, but that's my hope. It's still painful. Well, the adrenaline rush out of pain as we come back to center. Jennifer, you got to stay awake. Thank you. She was thinking of adrenaline rush. Okay, you're going to have to, at some point, channel some of that frustration into resolve, self-discipline, aggressiveness, and I'm going to make it work. Interestingly, as we talked yesterday in the bridge meeting, and we talked about the difference between Bridge 1 and Bridge 2, and you get talked about occasionally, as they do in Bridge 1. And one of the things that we are trying to convince in Bridge 1, that how much you have to care, how much you have to work at it and make it something that you are willing to do. And it's something that those of you who survive in Bridge 1 sort of take for granted at this point. It's also something that I'd like to take a 2x4 to some of you and say, yes, that if you had that resolve and that aggressive feeling for it, it would benefit you enormously right now because it's not quite there. And that's a big difference because we take Math 10 and we go to 20 and you don't have that outside kind of cracking the whip to keep you in line. You have to do it from your insides, what's meaningful to you. So the pain, yes, is there. And I don't care how far you go in mathematics or how good you are at mathematics, you will hit the walls. And then the question is, how do you hit the wall and what do you do? Are you aggressive? Do you really fight it? Is it important enough for you to do it? Interestingly, when I did a doctorate, that same kind of comment was made to me. How much do you care? How much do you want it? How much are you willing to put everything on the line? Because if you aren't willing to, you won't finish. And I could make that same argument. So part of my concerns here, you have to want it. And there are parts here that do get a little bit confusing, a little bit tough, but it can be done. There's only one more problem I want to just reference. This is Natalie's distributive property, and I don't think I need to say much more than that, so let's just briefly do it, and in 45 seconds I will be done. Notice how we take the number outside and multiply it times everything in inside, following the little arrows, and then you add the garbage that's left. Do the product. So with that, I'm hoping that you'll do that. Tomorrow, I'm going to focus on questions from here and questions from 6-2, and we'll spend a lot of time on Q&A tomorrow and with the tutorial on Friday. And Jennifer, as we close with Rod Stewart.